Hi, welcome to another edition in this series of videos. Taking another look, or a different look, at conventional physics and its explanations for phenomenon and such. Trying to find a deeper, better answer. It doesn't even really have to be all that deep, right? I mean, just less wooey. Less non-physical, more physical explanation. So I left off with a bit of the paradox of two wires with current flowing in the same direction, and they attract when you're supposed to likes are supposed to repel, and then when they're going the opposite direction, they attract. Repel when they're supposed to attract, like opposite magnets. So, I probably should do this. I did, lots of sloppy drawings of things. So the idea is a conductor would have these little magnets, going around the perimeter, and the magnets would represent the atoms in terms of their electrons and protons and how they are aligned. And I think I like this better this way. It's complicated being a presentator. Anyway, so I've reduced that in these drawings to something simpler. So you have to imagine a million of these little magnets going around in a circle. And the idea is the compass needle would go around just the same way. The black end this way. This is the right-hand rule, essentially. And with like wires, with the current going the same direction, it ends up that you're on the left side of this one and on the right side of this one, which means they're going essentially in opposite directions. So this one's going black to red, and this one's red to black. You can see there. So the compass needles are opposite, which means you would have attraction, which is all quite sensible. I would argue the cause for that is you can see it if you simplify it. So if you simplify it to a square, you can kind of see that this magnet, its pole is pointing in a direction, and it's the opposite direction of the pole on this magnet. And likewise over here, the poles are opposite. And that's what's really responsible for the orientation of the compass needle, is that this side is more black and this side is more red in terms of the energy, which means the compass needle goes the opposite way, as it should. And that's the bias. That's the thing that biases it. So you can sort of think that it's like little shark teeth going around the circle, that one end of the magnet sticking out a little bit, sticking out a little bit, sticking out, because it can't be flat. It's going around in a circle. So you can sort of see that they'd all be a tiny bit at least, and they'd all have that jagged edge on one going in one direction, essentially. And when you put them next to each other, you would see that that's going to end up giving you exposure to the opposite ends and creating attraction. And then if you have it reversed, that is, the magnets are oriented in the opposite direction because you have the current going the opposite direction, then you'd have exactly the opposite effect of likes against likes and repulsion. And so that sort of explains why this one circumstance creates the illusion of the paradox of likes not doing what they're supposed to do, which is repel. It's really just because of this left-right thing and the fact that you have a circular magnet, technically. Probably. The way the electricity is moving, that's the rule. So this right-hand rule, I don't have an explanation for why it exists. I mean, why, when current goes one way, the polarity of the magnets goes red-black, and when the current's going this way, it's black-red. Obviously, it has to be opposite. So in that sense, it makes sense, right? They can't be the same way for both going in and going out. It has to switch like a mirror. It has to switch the two sides. So you can't avoid that. And maybe that's all it comes down to. But why is it one way rather than the other? It's like asking, why the water turns a certain way in the toilet. It's pretty much a rule, and that sort of comes down to something about where the center of the gravity of the conductor is, or some other kind of thing. Well, anyway, that's for another day. I just want to clarify the mechanism, I would argue, that is responsible for the paradox. All right, continuing with the real video now, or continuing with the lecture that provoked this issue. How come that's not right? I guess you have to do that instead. Okay, that seems okay. All right, hopefully we're all right, and we can just begin where we left off. Hopefully. Yeah. I like hoping. Oh dear. Yeah. There we go.
So you've seen that we can, with a magnet and a moving charge, that we can change the direction of the moving charge. Force on the moving charges. If you have an electric field as well as a magnetic field, then of course you have also the electric.
So he does say the word force now and then, which is nice, but they don't have an explanation for what the force is made of. They don't have any origin for its creation. They don't have any energy to explain what this force would be made of. But even to say the word force, I mean, it really does tell you that the force, he's not just saying field. He's not saying something ambiguous like the electric field. I mean, when you use the word force, you're sort of implying something, not nothing. And, they have nothing. And I'm just saying this provides you with a something. The external world is pushing. And these mechanisms filter that pushing force. And it explains everything, if you just think that way.
Force. And so the total force on a moving charged particle would then be Q times the electric field vector.
So again, a moving charged particle just means essentially a little tiny balloon with charge on it, okay? I mean, that's what an electron is. And that's what a proton is. They're the smallest little balloons you could make with charge on them. So when he says a moving charge, it's nothing essentially special about a moving charge other than it's a charge. That is, it's filtering the energy. It's taking the red stuff and perpendicularly it, and it's reflecting the black stuff. So if it comes into contact with another black thing, they're going to reflect off of each other, and if it comes in contact with a red thing, they're going to attract each other.
Plus V cross V. And this, of course, we've seen before. An electric field can do work on a charge.
So just understand they have two fields now, and he's the electric field and the magnetic field. It's all the same field. It's all the same force. So these are really unnecessary distinctions.
Remember, Q delta V. It can be positive, it can be negative, but it can do work. It can change the kinetic energy of the charge. Magnetic fields can never do work on a moving charge. And the
okay, that's just wrong. So, and I would argue it's calculably wrong, because you can take this moving charge and you can change it, accelerate it up or accelerate it down. You don't just move it up or move it down, you accelerate it. And it's just, I think it's just wrong to say it doesn't do work. It does do work.
The reason is that the force is always perpendicular to the velocity v. And so if the force is always perpendicular to the motion, you can change the direction of the motion, but you can't change the kinetic energy.
Yes, you can. Just like the Earth. Well, the Earth is a good example, right? You wouldn't say gravity isn't doing any work, but obviously it's not going to increase the velocity in the sense it's not going to give it more forward momentum. It's giving it a different momentum. But there's work involved in terms of bending it from this to this. That's work. So, let's see, how's another way of saying it? Well, clearly later in this thing, he's probably going to get to some things where they're accelerating particles with magnetism, and obviously you couldn't accelerate them with magnetism. Well, I don't know if they're accelerating, they're confining them with magnetism. There's probably an example somewhere. I'm just saying, if I take a static charge, it's just not moving at all, and I put it in a magnetic field, it's going to move. And all of that movement was because of the magnetism. So I think it's just wrong to say it doesn't do work. Of course it does.
So that's a fundamental difference between the electric force and the magnetic force.
I think it's just an unproven declaration. It doesn't even have somebody's name on it. Some Dutch guy says so. Well, where's the proof that this is written in a stone somewhere, that magnetic fields don't do work? I think, of course, they do.
So now I want to calculate with you the force on a current that runs a wire I through it, and we have a magnetic field B. So we're going to be more and more quantitative. This, by the way, is often also called the Lorentz force, just a combination of the two. That one certainly is. So let us start with a wire, and the wire runs a current through. Here's the wire, and the current is I. And let's say at this point here, we have a magnetic field B.
At this point here, see, this is where it's going to get a little messy. A magnetic field caused by what? A magnet? I mean, let's see what he draws. I fear that there's not going to be an explanation for what exactly is causing the field. He's just saying it goes in this direction, when magnetic fields, as we just demonstrated, have a plus and a minus element, a red and a black, a north and a south. And it's sort of important which one is where.
The magnetic field could be different along the wire, in principle. Here, I have a charge plus dq, and this charge is running through the wire with a drift velocity vt.
Alright, so this is all dependent on their understanding of what's causing the effect. I would argue that the charges are not causing the effect, in the sense that the atoms are causing the magnetism, and the force is what's moving through the wire, not a charge. So, I can't say much about this except, okay, you picking these variables that I don't even think are real variables is fine, because they're sort of related to the real cause. So the real cause, all right, the way this should be labeled is, you have atoms in the conductor. The atoms will now be polarized, and that polarization, depending on the current, will become more and more coherent. That is, more and more alignments, creating more and more magnetism, because now you're aligning the atoms, and by aligning the atoms, you essentially are turning the wire into a magnet. Now that'd be one way of representing this, and he's got another way of representing it, because he's saying there's some sort of charge moving through a wire.
Let's first think about what happens if the current is zero. If the current is zero at room temperature, these free electrons in these wires have huge speeds, 3 million meters per second, way larger than the drift velocity.
Alright, so again, they say these things, but I don't think they have any evidence of these things. So, just as they don't have any evidence of their standard model that anything really is moving and electrons are busy working and going, electrons don't have any, electrons aren't photons. They can't just move. They don't have any perpetual velocity. Can't shoot one through space. They run out of gas. That's wherever we shoot photons, where we see it, run out of gas. So even in a vacuum, they run out of gas. Let's see how to put it. Yeah, I mean, that's as simple as you can say it. So, I mean, these models they have are incomplete, in the sense that they have no explanation for where all of the energy comes from to maintain what they're arguing is happening. So I would be just as suspect their claim that the atom has all this motion in it. That's not the photons, and just the photons. They're the only thing moving. I mean, this is the irony of this whole conversation, is that the only thing we know in the universe that has perpetual motion are photons. are these little bits. And we know that these little bits move the same speed as gravity and the same speed as magnetism, and same speed as the electric field, if there were such a thing, the electric force. So and then we know that the stuff moving through the wire almost can approach that speed. Depending on how efficient we make that wire, it can almost approach the speed of light. So clearly most of the motion must have something to do with stuff moving the speed of light, some of this photon kind of stuff. It's not electrons moving or atoms moving or something else moving, because they can't go that fast. So obviously they're playing a small role where the force is playing the main role. And that explains where the energy comes from. The universe, all the energy in the universe, all the stuff that's moving is only moving because of photons, because of the thing with perpetual motion that nothing else has. Nothing else has except big matter things that you push into space that have a photon engine inside of them. They actually do have, it's a photon torpedo, so to speak. When you throw something into space, it's essentially a photon torpedo, because the way the matter has been accelerated has created formations inside of it that are taking advantage of the motion of photons. But it's photons that are pumping the bicycle wheel. They're the thing, they're keeping the thing moving through space. Photons are all the energy. Anything that's moving is moving because of something photon-like pushing it along.
But they are in all chaotic directions. Random motion, it's a thermal motion. And so on each individual charge there will be a force, but they average out to be zero. It's not until I run a current that these charges are going to walk through with a very slow drift velocity. And now, of course, the net force is not zero.
So another way to metaphor it is, look, the system is in chaos. You run the current through, it can't be in chaos anymore because it's pressurized. So when there's not much pressure, everything's loosey, and when you tighten the pressure, nothing can move. So it's another way of looking at it, is if I have some kind of thing that no pressure, the loose string can blow in the wind kind of thing, and tight string, no blowing in the wind anymore. It's impervious to that kind of crap. So the more pressure you're shoving, the less chaos there can be, because everything's getting tight.
So let's have this charge dq that moves in this direction, and so that gives me a current. And let this angle be theta between them. Theta is going to be important because it's a cross product between velocity and b. That means the sign of this theta comes in later.
Yeah, well, technically there's really no complexity to that theta, because it really should be 90 degrees, technically, at any one point.
You will say, I hope you will say, well, listen, man, this is ridiculous. Positive charges don't move through wires. It is the electrons that move through wires. They are responsible for the current. And electrons have a negative charge, and they go in this direction. You're right. Perfectly fine. However, a negative charge going in this direction is mathematically exactly the same as a positive charge going in that direction. In both cases, do we agree?
Exactly. So that's just sort of the problem with your math, is that it doesn't bind things to rules, and in a sense, it's just a metaphor for the reality, because the reality is the more complex fact that the protons don't do as much of the function of current going this way or that way as the electrons, but they are inversely impacted by what the electrons are doing. But they're not the ones moving the force.
That the current is in this direction. So I have preferred, for mathematical reasons, to take a plus d cubed charge going in this direction, rather than taking a minus d cubed charge that goes with the drift velocity in that direction.
Yeah, I don't know. So you just decide to confuse everybody for no good reason. Oh, okay. Go ahead, I guess. Do something against every convention that you've just taught everybody about, all this rules about right-hand rules and all this, and now we're going to do left-hand rule. Okay.
There's no difference at all in the outcome that you will see. So on this charge, there is a force, dF, this magnetic force, and that is the charge, dq, that equation, times v cross b. Well, v was that drift velocity, and here is the magnetic field at this location.
So the drift velocity is just another way of quantifying the voltage. The drift velocity would increase as you increase the voltage, and so they're just using this drift velocity as a way of putting a number on voltage, but it's just voltage.
The current through the wire, everywhere in the wire, must be dq dt, because that's the definition of current. How many coulombs per second? Current is always dq dt. So I can also write this as I dt times Vd cross B.
IDT. So we got rid of the dq and replaced it with IDT. So that's the time factor. And then drift. So that'll give you volume. Right, so time times the speed of the drift would give you, the drift is going to decide volume, the drift speed. And it's just a matter of how much time you have drifting will tell you how much current. Okay.
But I remember 801, that Vd times dt, that is a speed times a time, is a distance. And I call that distance dl. It's a distance along the wire. I will put the distance in here now because I don't want to clutter up my drawing. So this charge in time dt moves over that distance. That's a vector, 801. So I can write down for this product, I can write down dl.
Well, yeah, but he made this crooked line so that nobody's going to want to try to do that integral. That'll take you forever.
So I can also write down that df of b equals I times dl cross b. What is this telling you?
All right, cross B is the magnetic field that he said was created by what? So I still don't understand how. I still don't understand. And the magnetic field was created by a dq. So I don't know how a dq is creating a magnetic field when that's supposed to be an electric field. But whatever. Let's just play along.
This is the force of a wire over a small segment of the wire which has length dl. I is the current through the wire, and B is the local magnetic field at that location dl. That's what it means. And if you want to know the entire force on the wire, you have to do the integral along the whole wire. And so you have to do an integral along the entire wire, and at every portion dl you have to determine what B is, and you get then a force, which is a vector, and you have to add those vectors vectorially. Could be a pain in the neck, but that's the basic idea.
And for what purpose? Why would I want to have this idea? The idea. Why would I want to have this idea? That's a little thing, just little. I mean, these are little complaints. Don't get me wrong. Just, I'm impressed. People know more than one language. Great. But just little things like that, like saying the word idea. Idea. You think somebody would say, hey, it's idea. No big deal, but come on, idea, not idea.
So now, I want to calculate what the force was, wire roughly, when we ran 300 amperes through there. And I make a geometry so simple that we can execute that integral. This was the wire.
So now he's used a straight line. Yeah, so I don't know. I don't know what the crooked line was for. I don't know what the whole thing, I don't know what this example was supposed to demonstrate, but sure as hell confused me. Thank you.
And we had
this was the wire, and we had a current running through here, which, oh, okay,
Current was running through here, which was 300 amperes roughly.
I got fooled by the closed captioning. That's funny.
And we have a magnetic field.
I suppose I can turn that off, right? I can just click this and turn it off. I don't know, it probably helps, right? Yeah, it probably helps. Can't hurt.
Which was right in the gap there. That magnetic field, B. And that was 0.2 of a Tesla. 2 kilogauss. And that magnetic field was only operating here. Wasn't operating there. And I make the assumption, which is a simplifying assumption, that that magnetic field was constant over a portion of the wire which was, say, only 10 centimeters. And so I assume here that I have a length which is 0.1 meter, and that in this range here, the magnetic field is constant. I just want to get a rough number for the force on that wire. So now I can integrate that equation very easily, because I have assumed that the magnetic field is perpendicular to the direction dl. The dl is now in this direction. So the sine of theta is 1, so I don't have to worry about that. And so I simply get that the force on this section L, that force, call it F of B if you want to, is the current I, which we have there.
All right, so back to what I was talking about. So you have to kind of think about the magnets are rolling around the conductor. Okay, so they're going north, south, north, south, north, south, north, south around the conductor. And so they're showing their head this way, which is all black heads, and their tails this way, which are all red tails, as they're going around the wire. Right? You can sort of think of it that way. You're seeing more tail as they're leaving, and you're seeing more heads as they're coming towards you. They're not moving, but I just mean that's how you're going to see them, because they're not on a straight surface. They have to kink. And so what the magnet's going to see is the north end, let's say, is here, and it sees, the black end's here and the red end's there, and it's going to push this way down. The negative's going to push the bottom of the wire, and the positive's going to attract the red end as it goes. So it's going to cause it to spin down, and then it'll spin up the opposite way if you reverse the magnet. So it's just going to react to the fact that there's a difference. There's a dipole, essentially. Now you've created polarization out of a circle. So understand, the fact that the atoms can't make a circle, that they will at least, is essentially telling you, that they're planar, that they're not bending. And it's a tiny, tiny little difference, but it's millions of little tiny differences, and that adds up. Little bits of that tail showing, or little bits of that extra head showing, and maybe not the best metaphor, but anyway, well, it's not even a metaphor; it's just the way it is. So is it going to add to that something important? But that thickness of the wire matters, because now it's essentially a dipole, so it's a magnet. And if it's in the field the wrong way, and it can't flip, it's going to react by going up or down.
We get the length L, which is this length, multiplied by the magnetic field. There is no sine I anywhere because the angles are 90 degrees. And so I find that force is 300 times 0.1 times 0.2. So that is 30 times 0.2. That is about 6 Newton. 6 Newton is more than the weight of 1 pound. And so it is not so surprising that when I turn this current on.
So that's good to know. 6 Newton is the weight of the weight of more than 1 pound. So Newton is like 5 ounces of force. Less than that. 6 into 16. Yeah, I can't do that. Yeah, that's too complex. All right. So I'm trying to go over rather than under, so I could jump it to 18 ounces would be 6 Newton, And then you go 6 is 3, so 3 ounces would be a Newton. Maybe I should write that down. Then I'll know what a Newton is. Anyway, do I have to say anything about this? I don't think I'm just saying he's doing an approximation, and sure, why not? I could probably make up some sort of bibble-babble about how to estimate the force.
That something all of a sudden pulls that wire down with a weight that is equivalent of a little more than a pound, almost a pound and a half actually. And so it's not so surprising that these supports fell over. So you see that you can turn this quantitatively, provided that you make some simplifying assumptions about the uniformity of the magnetic field and about where the magnetic field is present.
Right, so a Newton is like 4 ounces, just to be safe. 4 ounces.
Now, I want to talk about the great 802 motor contest. This contest is not part of 802X. We're about to start.
I don't even know what 802X is. I don't even know. Why did they put an X on it? I know it's different. It's better in some respects. You know, some of the experiments are filmed better. But what the hell is it? Yeah, I have no idea.
So this great 802 motor contest. You got an envelope today, and I'm going to start to tell you slowly about the physics. The goal is ultimately to build a motor. If I have a current loop, here's a current loop. Current comes in at A, and I'll try to make you look at it three-dimensionally, which is not so easy. This is the current goes out here at D. This is a current loop. Current goes through here, goes through here, goes through here, and returns here. And we have a magnetic field, and we will assume that the magnetic field is constant throughout in this direction. There is a force right here on this wire in the direction I cross B. That force is up. There is a force here on this wire, which is of course down. Magnetic field is in the same direction. The current is in the opposite direction, so the force is down. If this wire has a length A, this wire has a length A, that force, the magnet...
So again, the same rule applies. I'm just giving you an explanation for the right-hand rule, is the fact that when the current's going in a direction, the top will be the black end of the magnets, the bottom will be the heads, will be the reds, and when it's coming out at you, it's the reds and the opposite. So it's just about how those magnets are tilting. And that's going to determine whether it goes up or down, because it's going to decide whether it's a magnet facing north-south this way or north-south the other way. North-south or south-north.
The magnitude of that force is the current through the wire times the length of the wire times the B field. We just derived that. There's that integral. We just assume that the magnetic field is constant everywhere here. They're at 90-degree angles, so the sine of theta is 1, and so that's the force. What is the force here? What is the force here? Well, it's 0. 0 here, and it is 0 here. Why is that? Because the cross product is 0. No matter how you look at it, you can say dl and b are either in the same direction or in opposite directions. You can also say the drift velocity and b are either in the same or the opposite direction. It's all the same thing. There is no force here, and there is no force here. Because that equation that we had that gives us the magnetic force becomes 0. The sine of that angle is 0. So what's going to happen with this thing? Well, there's a torque on this system. There's no net force, because this force up is the same as this force down. But
so again, he says there's no field there, but that's just because those are the parts where you have equal but opposite reaction. So it's not like there's no force. It's just the force is going to be proportional on both. There won't be any more up than there will be down or whatever. So it just ends up the forces cancel on those perimeters.
there is a torque which wants to rotate it in counterclockwise direction. And the magnitude of that torque is of course this force, remember from 801, times the perpendicular distance between these two forces. And so the magnitude of that torque is I times AB times B at this moment in time, when the forces are this far apart. Now this is going to rotate, and so as they rotate, these forces come closer, and so the torque will become less. Still, it wants to rotate counterclockwise. And there comes a time, 90 degrees later, that the torque is 0. And I will try to...
It's even again. So there's a point where you're in between the magnetic force and there's no force. So you have to have a disproportion to have torque. You have to have pushing away and attracting, and once you get to a mean point, then the compass needle wants to stay there. It doesn't want to move. You move the compass needle and then it says, I'm going back to north-south. You move it this way, no, I'm going back. You move it this way, I'm going back. So it's a compass needle will demonstrate the effect, essentially, of there's a point that's equal. The balance is equal.
Make you see that again in a three-dimensional way. It's not so easy for me. Now this is D. This has become D. The current always leaves at D. I'll try to make you see this three-dimensionally. It goes like this. The current comes in here, at A. So we get this, and we get this. Doesn't look so bad. Then the magnetic field B has not changed. Uniform B in the same direction. So the current now comes in through A. It has not changed. The only thing is that the loop has rotated 90 degrees. If now I ask you what the forces are, you have to go I cross B. I cross B. If you do I cross B here, I cross B, you get a force which is towards you. Here, you get forces which are in the blackboard. Here you get forces which are up, and here you get forces which are down. At home you will have some time to use your right hand and do the...
So, you obviously don't have to go to the trouble to point which way you have forces, because it's, technically you don't even have a force. It's the thing's being affected by the force. And what you have is whether that B field is equal in terms of its effect. And that's all you've said. You've gotten them into the halfway point. It's equal exposure. They have no reason to move because they're getting hit top, bottom by the same amount. So they don't go anywhere. They have no, it all evens out. But it has to do with the field being balanced, not the wire being balanced.
I cross B. And you will see then that indeed all these forces are in the direction that I put them. So now there is again no net force on the system. There was no net force here either, but now there is no torque either. So now the torque has become 0. If we rotate it a little further, it is possible when we start this motor, starts to rotate counterclockwise, comes to this position, torque goes to 0, but it has enough inertia, so it rotates a little further. And now the torque will reverse. And this is something that I leave you alone with. I don't want to make another drawing and convince you that it reverses, but it's easy to see, because take this thing and just flip it over.
Yes, all you need is the compass needle. The compass needle, you can't make the compass needle go all the way around. The compass needle just goes back this way. It goes back to north, so you'd have to push it all the way to past halfway to get it to swing the other way. You still wouldn't get it to swing. It would still swing back this way. It would still go the shorter distance. So that's all he's basically saying. The compass needle, if it overshoots, it's coming back. It'll just wobble. It can't go anywhere. Can't keep spinning. When you push it, it's not going to keep spinning.
180 degrees. The magnetic field hasn't changed, but the currents in these two sides have changed direction now, because whatever is D is here and A is here. And so the torque reverses, and so it goes like this, and then it comes back. And that's not much of a motor. Current meters are very frequently used. They are in your cars, many more than you think. Your fuel gauge and your temperature of the cooling water are current meters. And the current meter works as follows. We attach to this loop a needle and we calibrate it here. And you can read how many amperes are going through this meter. It wants to go counterclockwise. Here we attach a spring, and the spring produces a counter torque, and so the needle will start to deflect but come to a halt. But if you double the current, it will go further. That's the way that a current meter works. And your fuel gauge in your car is a current meter, except that the level of the fuel is somehow converted into an electric signal, and then it's sent through a current meter, and that's what you're reading. It is, of course, calibrated in terms of how much fuel you have.
Well, the somehow is simplest form is a cork floating in the gas, and as the cork moves up, it turns a magnet, and blah blah blah.
And your temperature gauge is calibrated in terms of degrees, whatever, Fahrenheit or whatever. So these current meters are very common even when we're dealing with something that has nothing to do with current. How do you build now a motor that works? How do you get over this torque reversal? Well, it's not only the torque reversal that is a problem, but there is also the problem that if you could keep this going around, that these two wires would intertwine and they would break. If you rotate it around 100 times, you can see what happens at A and D. It will break. So you have to think of a design whereby you have slipping contacts, we call them brushes. Suppose I have here a conductor which is connected with A, physically soldered to the wire at A. And here I have a conductor which...
See, this was the whole Tesla thing and everything else. You get into this brushless motor idea. The idea would be is you put a permanent magnet inside the armature. So you're spinning a permanent magnet around an electric magnet. And the electric magnet is AC current, so it's phased. And then the phasing takes care of it. But those motors are intrinsically incapable of doing any speed control. They'll go at one speed and that's it. That's the only disadvantage. But you eliminate the need for brushes. This idea of having the two wires turn and still connected to the electricity.
This D. So the loop is where you are. Solid wires coming out the loop is here. But now the battery, plus side of the battery is here, and the minus side of the battery of here, and this is a slipping contact. In practice, we call them brushes. So that immediately takes care of the problem that the wires wind up. But there's something else which is very clever about this design. If the gap between A and D is an insulator, then what's going to happen when this rotates 180 degrees, A, which now is on the positive side of the battery, this is negative of course, A is now on the positive side of the battery. If you rotate 180 degrees, A will be on the negative side of the battery. So now every rotation, the current will all by itself change direction, and we call that a commutator. And so now...
So, compass needle example would be, the compass needle won't spin, but if every time I got to this point, the Earth's magnetic field switched, then the compass needle will just swing around because it's saying, hey, it switched, I'll go that way. And so it solves the problem. And so it keeps switching every 180 degrees. You keep switching, and then you go around and around and around. And the motor is invented.
What's going to happen is, now the torque reversal will not occur. If at the right moment the current switches direction, the torque will always want to rotate the loop in exactly the same direction. And that's the idea behind a commutator. The Great 802 Motor Contest. You have an envelope. When you open it up, don't do it now. You'll find in there a copper wire, 2 meters insulated copper wire, 2 magnets, 2 paper clips, and some wood. And the idea is that you try to...
Okay, 2 magnets. So you put the magnets, the wires, to create a bigger loop, because just a regular piece of loop isn't going to be much of a motor. You need more field effect. You need to capture more of the magnetic effect. But I guess technically you could make the motor both ways. You could put the magnets on the spinning part. Well, I'll have to think about it. But I'm sure you could do it. You just have to think about how you do it.
Build a motor that runs as fast as possible. For every 100 RPM, an RPM is a rotation per minute. For every 100 RPM, I'll give you 1 credit point with a maximum of 20 credit points.
Yeah, the problem is without AC current, you can't do it that way, so never mind. You have to do it the standard way. The coil of wire is where the loop is, and so you're spinning the coil inside of the 2 magnets.
So if your motor runs 2,000 RPM or more, you get 20 credit points. That is equivalent to 2 homework assignments. And these credit points come over and above your course grade. You have my word for that. We'll give you a final course grade, the way that you've seen in the ground rules, the first handout, and we add your motor contest, what you deserved. For every 100 RPM, you get 1 point plus with a maximum of 20. And we're going to test these motors on the 2nd of April.
It's probably only like 1% of your grade, so it's probably not all that spectacular. I'm sure just the final exams, the 4 tests that you take, are probably 80 or 90% of your grade, and the only 10% is left over for these homework assignments.
And I gave you a handout in which I give you some hints, some ideas. There's one idea that I gave you which you may ignore, and that is to overcome the torque reversal. You can build a commutator. That's really not easy. Not only is it not easy, but when you build a commutator, your system may get a lot of friction, and you may lose more than you gain. There is an alternative solution, which I mentioned in my handout that you picked up today, and that is that you design your motor in such a way that when the torque reversal occurs, that there is no current running anymore. And when it is half a rotation further, the torque is there again, the current is there again. So for half the time, you stop the current. You'll see that's very easy. I give you some hints how you do that. So you have to weigh that again.
So it's just how you make the brushes. So yeah, so you really don't have to go, you just have to go 90 degrees past, and then you can put the current back on, and then you go to flip here and turn it off again for that. Yeah, so that ends up being half the time. Yeah. 2 wedges is half the time.
The possibility of building a commutator. The bottom line is, the maximum is 20 credit points. That's an equivalent of 2 homework assignments. You get it over and above your course grade. And it's also great fun, believe me. What more do you want? To do physics, get credit, and have fun. That's what I do every day. It's the great thing about physics. We have 5 minutes left, and in those 5 minutes, I'm going to demonstrate to you a motor. What you see there is a current loop. I'll try to make you see it 3-dimensionally. This is the current loop, and we're going to run a current in this direction. And we here have a magnet, north-south. Magnetic field is in this direction.
Yeah, it'd be interesting to, so this is really just more loops of wire, so it doesn't show that part. But it'd be interesting to figure out whether it matters how you arrange those pieces of wire. You know, because I would say technically the more in alignment they are, the better. And the more flat they are, the better. So, but anyway, we'll see.
And we here have a magnet, north-south. Magnetic field is also in this direction. I'm going to run a current through here, and if the current is in the black box,
obviously there's no magnetic field in a direction. The north end is creating the black stuff, and it reflects black stuff. The south end is bouncing off the red stuff and absorbing the black stuff, and that's all that's really happening. There's no direction this way thing happening.
I cross B, I is in, cross B, force is up. This side wants to go up. If this side wants to go up, since the magnetic field is in the same direction here, but the current is 180 degrees in opposite direction, this force will be down. And so there's a torque on it.
So the wires are just, you have the current going in the opposite direction in the wire. So one wire is going this way, the other wire is going this way, and so they're exposing the opposite ends, blah, blah, blah.
And you will see that. You will see that go like this. However, when it's 180 degrees and it swings hereby, it wants to go back because of the torque reversal. So that's the first thing that I want to show you. And I think I don't need any changes in the light. So here we have this loop, and here we have the 2 magnets. The magnetic field is by no means uniform, by the way. It's very strong here, and it's very strong there. And now I have to power that. There we go. I can't, yeah, I think I know that this one will come up this side. I'm fairly sure that I have the directions right. Let's first take a look at it. There it goes. So when it's here, notice, it goes up. But now, if I power it here again, it wants to go back. So here, it wants to go up, and here, it wants to go back. So we've got to do something. And that something is a commutator. So if we can somehow reverse the current when it's here, then it wants to go down again. I'll show you that. So now it's here, and I will drive the current in the other direction. You ready for that? You notice it now wants to go down. Now it wants to go down. But when it's here, have to reverse the current. I want to go up. And if I do that with my hand, I can see whether I can keep this rotating. It may take me a while, but I'll do my best I can. There it goes. Switch, 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 switch. Yeah, got it. Yeah, got it. I'm a commutator. And this motor is going at least 60 RPM. That's 1 credit point for me for this course. Thank you.
Okay, a little bit of theater, whatever. Useful, mostly. So anyway, I think that's about covers it. I don't know if I need to add anything. I shall go to the black screen. Alright, so I think we've done our job, and so on to the next adventure in physics and such. Frame rate on this camera's gotten pretty poor. Well, anyway, can't have everything. Try to fix that. I don't know. Like, I don't know if I can. Just reload it or something. We'll see. Till next time.